The topic for today is Laplace transformations. Now, the Laplace transformation is a specific instance of a broader notion called integral transformations. And I have Wikipedia up and running here, and they give us a brief description of what an integral transformation is. You're going to start with a function f of t. You're going to multiply it by some function of t and u, integrate with respect to t, and what you'll get is a function of u. So you essentially change a function of t into a function of u. Um, why would you want to do this? Well, let me scroll down here. The motivation is easy to understand, right? It is quite often the case that you're working on a problem and it's hard to do. And what you need to do is you need to change it into a different problem, solve a different problem, and then bring it back. I do this all the time when I'm trying to solve algebraic problems and I don't really see how the algebra is going to work, or a trig problem or something. And what I do is I interpret it geometrically. I'll draw the graph of a function. I'll draw, a triangle if I'm doing trig, and I see how the pieces that I have are related within the geometry. I can then use the geometry to solve that problem and come back and then reinterpret it algebraically. This is something I just do all the time. It's interaction between functions and graphs and working back and forth that way. And these integral transformations are going to do a different kind of thing for us. And there's a bunch of integral transformations. Again, I'm just going to scroll down here and show you real quickly on this Wikipedia page. The different transformations just come from, let me go back up the top here, just come from a different choice of what function are you multiplying by. You're starting with f, you're multiplying by this k, it's called the kernel. What kernel are we using? Well, where's that, Abel seemed to think that using this kernel did something for him, helped him solve certain problems that he wanted. Fourier used a couple, this one, or the sine transform, or the cosine transform. Henkel, Hartley, Hermite, Hilbert, Jacobi, Laguerre, I'm sorry, my French is terrible. Each of these people have come up with these different things that they multiply by, then do an integral, and transform a function of t into a function of some other variable. They're using the other variable as u here. We will use s, but whatever. There's all kinds of things. The Laplace transformation is the one we're going to look at. We're going to multiply by e to the, well, again, I said we're using s as a variable, e to the negative st. But there's just all kinds of different things that people have used to transform one problem into another problem. And just to make sure we properly cite our sources here, this Wikipedia page can be found here at this link. Okay, so now we want to give a definition for the Laplace transform and show how we can use it to calculate some things. Now, first of all, let me say that we use these Laplace transforms in a differential equations class because they're going to allow us to solve differential equations. Actually, the way they're going to do it is we're going to be able to transform a differential equation into an algebraic equation and solve like a polynomial equation and just solve for the thing that we need. So we go from solving differential equations to solving algebraic equations. We then are going to have to be able to interpret our solution to that algebraic equation as the solution to the differential equation. So there's a couple of steps that we're going to need to go through, but the first one is just getting used to what this Laplace transform is and how to calculate it. So here's the definition. If you're given a function, the f of t, then I'm going to define a function of f, which I'll call capital F. So not a function of f, but a function of s, where capital F is its name. So I use this notation, the Laplace transform of f equals capital F of s, and it is the integral from 0 to infinity of e to the minus st times f of t dt. Okay. Now, I'm hoping you watch some of the videos on improper integrals so that you have some notion of how we're going to do this improper integral from 0 to infinity. Okay. Now, not every function has a Laplace transform. The thing is, this integral needs to be a finite value. That sometimes, as you integrate to infinity, things diverge. So there's a question of what functions can and can't be used here. And there's a theorem in the book. I don't want to get into the details too much in this video, but it's essentially saying if this function f grows no faster than an exponential function grows, I mean, so you're multiplying by this e to the negative st, so you can cancel out a lot of stuff here because these decay really quickly for positive values of s. Um, So as long as f is not growing any faster than an exponential, then we can probably find some values of s that'll cancel that out so that we get some finite values on this integral. So anyway, let's do an example here. And all of a sudden my pen has no ink. Example, let's let f of t just be the real simple function like, oh, how about 1? So the Laplace transform of the constant function 1 is going to be some function of s here. And it's the integral from 0 to infinity of e to the minus st times 1 dt. Well, I can do this integral. T is the variable. S is considered, we're treated as a constant. So there's a u substitution here, and you end up with a minus 1 over s e to the minus st evaluated between 0 and infinity. You're actually taking a limit here. I like to just plug this in and see if it makes any sense to me. If not, then I'll have to maybe do L'Hopital's rule or something. So if I plug the infinity in, it looks like this. I'm plugging it in for t, so that's times s. I'm plugging it in for t, so I shouldn't be plugging it in there. That's an s in the denominator. That would the integral with respect to t. So then I'm plugging a 0 in, minus 1 over s e to the minus s times 0. Okay. Now, e to the negative infinity times s. Well, if s is a positive number, then e to the negative infinity is 0. So I want this to converge. So I want this to be a 0 right here. So there's a caveat that s has got to be positive for this problem. So as long as s is positive, this will be finite. And then this e to the 0 is just 1, and I get 1 over s. And so the Laplace transform of 1 is 1 over s, where s is positive. Okay. It's going to be quite often the case where in order to get this piece, plugging that infinity and trying to get this limit to be something finite, you're going to have to put a restriction on s. But that's okay. As long as we have some way of doing it, some values of s where this works, then we have a Laplace transform of our function. So the Laplace transform of 1 is 1 over s. Let's try another one. Grab another piece of paper. And let's try another example. How about f of t is t? Again, stay fairly simple. So then the Laplace transform of this function is, I'm going to call it capital F of s. The integral from 0 to infinity, e to the minus st times t dt. This section is a really good review of Calc 2. It's like you got all kinds of things that are going to show up here as integrals. Can you do it? Well, I think we can do this one. So what do I have? This is an integration by parts. U du, v dv. I start with u and dv. Let's put this as a t here, e to the minus st there. This would be dt. This would be minus 1 over s e to the minus st. I guess that's got a dt with it too. So the integral is u times v. So t, let's say negative t over s e to the minus st, evaluated between 0 and infinity. That's t between 0 and infinity. I'm reminding myself of that. Minus the integral of v du. So the minus becomes a plus. There's a 1 over s. The integral of e to the minus st dt from 0 to infinity. Actually, this integral right here without the s is the one we did in the previous example, right? That's that integral right there, which turned out to be 1 over s, as long as s was positive. So I feel comfortable just replacing that with, I still have to figure this one out, so I'll think about this one in a moment. So I've got 1 over s times, and that's just 1 over s. It's an s. Okay. So now what's happening here? There's a L'Hopital's rule thing that's happening here. That is, you plug the infinity in for t, you got minus infinity over s times e to the minus s times infinity, minus plugging the 0 in for t, 0 times e to the 0 plus 1 over s squared. We had to mention here that s was positive. Okay. Now with s being positive, this is going to 0 because it's e to the negative infinity, and this is going to infinity. And what's infinity times 0? Well, that's a L'Hopital's rule problem, right? Because technically you're not going, well, you are going to infinity, but the way we calculate this is we say you're going from 0 to b, and you're taking the limit as b goes to infinity. So this is big number over s times e to the negative big number times s. And there's a question of who wins. Does the infinity win or does the 0 win? And you can rewrite this into L'Hopital's rule, whatnot, but after a while you learn certain types of functions always win over other types of functions. The exponential 0 will beat the linear infinity any day. So the 0 here wins. This is 0. And again, this was as long as this is actually going to 0, so I need s to be positive. So my net result here is 1 over s squared, and the Laplace transform of the function t is 1 over s squared. I am going to do a couple more examples, but I'm going to do them in another video.